A neon lamp is a miniature gas discharge lamp. The lamp typically consists of a small glass capsule that contains a mixture of neon and other gases at a low pressure and two electrodes. When sufficient voltage is applied and sufficient current is supplied between the electrodes, the lamp produces an orange glow discharge. The glowing portion in the lamp is a thin region near the cathode. The larger and much longer neon signs are also glow discharges, but they use the positive column, which is not present in the ordinary neon lamp. Neon glow lamps are widely used as indicator lamps in the displays of electronic instruments and appliances. History. Neon was discovered in 1898 by William Ramsay and Morris W. Travers. The characteristic, brilliant red color that is emitted by gaseous neon when excited electrically was noted immediately. Travers later wrote, "The blaze of crimson light from the tube told its own story and was a sight to dwell upon and never forget." Neon's scarcity precluded its prompt application for electrical lighting along the lines of Mort tubes, which used electric discharges in nitrogen. Mort tubes were commercialized by their inventor, Daniel McFarlane Moore, in the early 1900s. After 1902, Georges Claude's company, Air Liquide, was producing industrial quantities of neon as a byproduct of his air liquefaction business. And in December 1910 Claude demonstrated modern neon lighting based on a sealed tube of neon. In 1915 a U.S. patent was issued to Claude covering the design of the electrodes for neon tube lights. This patent became the basis for the monopoly held in the U.S. by his company, Claude Neon Lights, through the early 1930s. Around 1917, Daniel Moore developed the neon lamp while working at the General Electric Company. The lamp has a very different design from the much larger neon tubes used for neon lighting. The difference in design was sufficient that a U.S. patent was issued for the lamp in 1919. A Smithsonian Institution website notes, "These small, low-power devices use a physical principle called coronal discharge. Moore mounted two electrodes close together in a bulb in, added neon or argon gas. The electrodes would glow brightly in red or blue, depending on the gas, and the lamps lasted for years. Since the electrodes could take almost any shape imaginable, a popular application has been fanciful decorative lamps. Glow lamps found practical use as indicators in instrument panels and in many home appliances until the widespread commercialization of light-emitting diodes in the 1970s. Description: a small electric current, which may be AC or DC, is allowed through the tube, causing it to glow orange-red. The gas is typically a Penning mixture, 99.5% neon and 0.5% argon, which has lower striking voltage than pure neon, at a pressure of 1 to 20 torr. The lamp glow discharge lights at its striking voltage. The voltage required to sustain the discharge is significantly lower than the striking voltage. This is due to the organization of positive ions near the cathode. Neon lamps operate using a low-current glow discharge. Higher power devices, such as mercury vapor lamps or metal halide lamps, use a higher current arc discharge. Low-pressure sodium vapor lamps use a neon Penning mixture for warm-up and can be operated as giant neon lamps if operated in a low-power mode. Once the neon lamp has reached breakdown, it can support a large current flow. Because of this characteristic, electrical circuitry external to the neon lamp must limit the current through the circuit, or else the current will rapidly increase until the lamp is destroyed. For indicator-sized lamps, a resistor typically limits the current. In contrast, larger-sized lamps often use a specially constructed high-voltage transformer with high leakage inductance or other electrical ballast to limit the available current. When the current through the lamp is lower than the current for the highest current discharge path, the glow discharge may become unstable and not cover the entire surface of the electrodes. This may be a sign of aging of the indicator bulb, and is exploited in the decorative flicker flame neon lamps. However, while too low a current causes flickering, too high a current increases the wear of the electrodes by stimulating sputtering, which coats the internal surface of the lamp with metal and causes it to darken. The potential needed to strike the discharge is higher than what is needed to sustain the discharge. When there is not enough current, the glow forms around only part of the electrode surface. Convective currents make the glowing areas flow upwards, not unlike the discharge in a Jacob's ladder. A photoionization effect can also be observed here, as the electrode area covered by the glow discharge can be increased by shining light at the lamp. In comparison with incandescent light bulbs, neon lamps have much higher luminous efficacy. Incandescence is heat-driven light emission, so a large portion of the electric energy put into an incandescent bulb is converted into heat. Non-incandescent light sources such as neon light bulbs, fluorescent light bulbs, and light-emitting diodes are therefore much more energy efficient than normal incandescent light bulbs. Green neon bulbs can produce up to 65 lumens per watt of power input, while white neon bulbs have an efficacy of around 50 lumens per watt. In contrast, a standard incandescent light bulb only produces around 13.5 lumens per watt. Applications. Indicator. Small neon lamps are most widely used as indicators in electronic equipment and appliances, due to their low power consumption, long life, and ability to operate on mains power. Most small neon lamps, such as the common Ni2, have a breakdown voltage of around 90 volts. When driven from a DC source, only the negatively charged electrode will glow. When driven from an AC source, both electrodes will glow. These attributes make neon bulbs a convenient locus voltage testers. They determine whether a given voltage source is AC or DC, and if DC, the polarity of the points being tested. Voltage regulation. The breakdown feature of neon lamps allows them to be used as very simple voltage regulators or over-voltage protection devices. In the 1960s, General Electric, Signalite, and other firms made special extra-stable neon lamps for electronic uses. Switching element, oscillator. Like other gas discharge lamps, the neon bulb has negative resistance. Its voltage falls with increasing current after the bulb reaches its breakdown voltage. Therefore, the bulb has hysteresis. Its turn-off voltage is lower than its turn-on voltage. This allows it to be used as an active switching element. Neon bulbs were used to make relaxation oscillator circuits for low-frequency applications such as flashing warning lights, stroboscopes, tone generators in electronic organs, and as time bases and deflection oscillators in early cathode ray oscilloscopes. Neon bulbs can also be bistable, and were even used to build digital logic circuits such as logic gates, flip-flop, binary memories, and digital counters. At least some of these lamps had a glow concentrated into a small spot on the cathode, which made them unsuited to use as indicators. These were sometimes called circuit component lamps, the other variety being indicators. A variant of the Ni2 type lamp, the Ni77, had 3 parallel wires instead of the usual 2. It was also intended primarily to be a circuit component. Detector. Neon lamps have been historically used as microwave and millimeter wave detectors up to about 100 GHz or so, and in such service were said to exhibit comparable sensitivity to the familiar 1N23 type cut whisker contacted silicon diodes once ubiquitous in microwave equipment. More recently it has been found that these lamps work well as detectors even at sub-millimeter frequencies, and they have been successfully used as pixels in several experimental imaging arrays at these wavelengths. In these applications, the lamps are operated either in starvation mode or in normal glow discharge mode. Some literature references their uses. Detectors of radiation upend the optical regime when operated in abnormal glow mode. Coupling of microwaves into the plasma may be in free space, in waveguide, by means of a parabolic concentrator, or via capacitive means via a loop or dipole antenna mounted directly to the lamp. Although most of these applications use ordinary off-the-shelf dual-electrode lamps, in one case, it was found that special 3-electrode lamps, with the extra electrode acting as the coupling antenna, provided even better results. This discovery received an application patent. Alphanumerical display neon lamps with several shaped electrodes were used as alphanumerical displays known as Nixie tubes. These have since been replaced by other display devices such as light-emitting diodes, vacuum fluorescent displays, and liquid crystal displays. Latching since at least the 1940s, argon, neon, and phosphide glow thyratron latching indicators were available, for example as self-displaying shift registers in large format, crawling text dot matrix displays, or combined in a 4x4, 4-color phosphide thyratron matrix, as a stackable 625-color RGBA pixel for large video graphics arrays. Multiple cathode or anode glow thyratrons called decatrons could count forwards and backwards while their count state was visible as a glow on one of the numbered cathodes. These were used as self-displaying divide-by-n counter, timer, prescalers in counting instruments, or as adder, subtractors in calculators. Other in 1930s radio sets, neon lamps were used as tuning indicators, called tune-ins, and would give a brighter glow as the station was tuned incorrectly, because of their comparatively fast response time. In the early development of television, neon lamps were used as the light source in many mechanical scan TV displays. Novelty glow lamps with shaped electrodes, often coated with phosphors, have been made for artistic purposes. In some of these, the glow that surrounds an electrode is part of the design. Color. Neon indicator lamps are normally orange, and are frequently used with a colored filter over them to improve contrast and change their color to red or orange, or less often green. They can also be filled with argon, krypton, or xenon rather than neon, or mixed with it. While the electrical operating characteristics remain similar, these lamps light with a bluish glow rather than neon's characteristic reddish-orange glow. Ultraviolet radiation then can be used to excite a phosphor coating inside of the bulb and provide a wide range of various colors, including white. A mixture of neon and krypton can be used for green glow, but nevertheless, green neon lamps are more commonly phosphor-based.